Monoidal categories and their representations, Lecture 15, Problem Session. Problem 1. For an algebraically closed field K, prove that there is a unique, up to equivalence, simple transitive module category over the monoidal category of all finite-dimensional K vector spaces. Solution. Assume that M is a module category over the monoidal category of all finite-dimensional K vector spaces. Assume that M is equivalent to the category of projective modules over some finite-dimensional K algebra, which we denote by A. Note that the monoidal category of all K vector spaces has a unique indecomposable object, namely the identity object I. So this is a one-dimensional K vector space. And the identity object acts on M as a functor which is isomorphic to the identity functor. Therefore, any object of K mod acts on M as a direct sum of functors isomorphic to the identity functor. One consequence of this is that the radical of M is stable under this action. The identity functor sends radical to radical, and similarly, a direct sum of copies of the identity functor also sends radical to radical. In particular, since we assume that M was simple transitive, so there are no proper invariant ideals, this means that the radical must be zero, because the radical is preserved by an action, so the radical is indeed a proper ideal stable under the action. So by simple transitivity, this must be zero. And when the radical of the category of projective modules is zero, this means exactly that our algebra A is semi-simple. A functor isomorphic to an identity functor sends each object to an object which is isomorphic to the original object. So in particular, an indecomposable object is sent to an object which is isomorphic to this indecomposable object, and this cannot be any other indecomposable object. Due to the transitivity of M, we assume that M is transitive. This implies that A must have one indecomposable object. Transitivity means starting from any object and applying the action, we can get any other object as a direct sum. So since K is algebraically closed, it follows that A is isomorphic to K. Consequently, the category M is equivalent to K mod. And now we can do the usual trick with the Untitled lemma. We take the identity object, we map it to an indecomposable object in M, and by Untitled lemma, this gives rise to a homomorphism from the left regular module over K mod to M. And since the unique indecomposable in the regular module is sent to the unique indecomposable in M, under this homomorphism, and the endomorphism algebra is preserved, it follows that this is an equivalence of module categories over K mod. Consequently, the left regular module is the only simple transitive module over K mod. And this completes the solution of this problem. Problem 2. Let K be an algebraically closed field. Let D be the algebra of dual numbers over K. So D is equal to the quotient of the polynomial algebra over K in one variable x, modulo the ideal generated by x squared. Let curly D be the monoidal category of all projective bimodules over D. So this means that curly D is the additive closure inside the monoidal category of all finite-dimensional DD bimodules of the regular DD bimodule D and the projective DD bimodule D tensor over K with D. Let M be a transitive finitary module category over D. Show that M has at most two isomorphism classes of indecomposable objects. Solution. For brevity, let us denote by F the indecomposable projective DD bimodule D tensor over K D. Let x1, x2, and so on up to xk be a complete list of representatives of isomorphism classes of indecomposable objects in M, a complete and irredundant list. Let us denote by Mij the multiplicity of the object xi as a direct summand in the decomposition of the object which is obtained by applying the functor f to xj. Then we can consider the k times k matrix M consisting of all these multiplicities Mij. So here I and j vary from 1 to k. Observe that if we take the projective dd bimodule d tensor over kd and tensor it over d with itself, then here in the middle we will have d tensor over d with d. This is a multiplicity vector space which is isomorphic to d, and this is two-dimensional. So you simply will get this bimodule direct sum with another copy of it. In other words, f composition with f is isomorphic to f direct sum with f. And in terms of our matrix M, this means that M squared is equal to 2 times M. Since we assumed that our representation Carly M is transitive, starting from any indecomposable object xi and applying our indecomposable objects in the monoidal category, which are f and the identity object I, so this corresponds to the regular dd bimodule d. So applying them several times, we should be able to get any indecomposable object xj from Carly M as a direct summand. From this, it follows that in the case when our matrix M is non-zero, which means that the action of f on Carly M is not zero, in this case, all integers Mij should be strictly positive. Okay, so in this case, we can use that m squared is equal to 2m, which means that m is a root of the polynomial x squared minus 2x, and the only roots of these polynomials are 0 and 2. So the matrix M has at most 2 eigenvalues, and these are 0 and 2. So these are the only possible eigenvalues for M. And in particular, if M is non-zero, it's a matrix with strictly positive integer coefficients, so it has a Perron-Frobenius eigenvalue. So then the only possibility for the Perron-Frobenius eigenvalue is 2. And in particular, 2 must be a simple eigenvalue. The Perron-Frobenius eigenvalue is always simple. This implies that the trace of M must be 2, because 2 is a simple eigenvalue and all other eigenvalues are equal to 0. So the trace of M is a sum of all eigenvalues with multiplicities that should be equal to 2, which means that the sum of all diagonal elements in M is 2, and they all should be non-zero, and they all should be integers. So since all entries in M are positive integers, it follows that the size of M is at most 2. So this finishes the case when our matrix M is a non-zero matrix. Now it remains to consider the case where the matrix M is a zero matrix. Then F acts on the category Carly M as 0. Let d tilde be the quotient of Carly D by the monomial ideal generated by the object F. Then in the quotient, the object F is killed. So what we have? In the quotient, we have only one indecomposable object, namely the image in d tilde of the identity object I from D. Of course, this object acts on Carly M as the identity up to isomorphism. And since M is transitive, so from any object we should be able to get to any other object by the action, but the action only consists of the identities, it follows that we can have at most one indecomposable object. So if the category Carly M is non-zero, it must have exactly one indecomposable object up to isomorphism. Combined with the previous case, we solved the problem. We showed that we have at most 2 indecomposable objects. Problem 3. Determine all possible matrices M with positive integral coefficients satisfying M squared is equal to 2M. Solution. From the previous solution, we already know that the matrix M is either 1 times 1 or a 2 times 2 matrix. If M is 1 times 1, then the only possibility is obviously 2, because 0 is not allowed. So we only can have 0 or 2 as the eigenvalue. 0 is not allowed because the coefficients should be positive. So the only possibility is 2. If M is 2 times 2, then the trace should be 2, so we have 1 and 1 on the main diagonal. And then if you write the other elements as A and B, then from the equation m squared is equal to 2m, we have the equation 1 plus ab is equal to 2. As both a and b should be positive integers, it follows that they both should be equal to 1, and the only possibility for m is 1, 1, 1, 1. So the answer to the problem, we have two matrices, one matrix of size 1 times 1, and it consists of the entry 2, and one matrix of size 2 times 2, and this is a matrix 1, 1, 1, 1. So this solves problem 3. Problem 4. Let M be a finitary module category over a finitary monoidal category C over an algebraically closed field K. Let A be a K-algebra such that N is equivalent to the category of projective A modules. Prove that there is a C-module category N, which is equivalent to the category of all A modules, such that the action of C restricts to the category of projective objects in N, and this restriction is equivalent to M as a C-module category. So we can lift the action of C from projective modules to all modules. Solution? So we define the category N, which is usually called the abelianization of M, as follows. The objects of N are all possible diagrams of the form X, arrow Y, where X and Y are objects in M, and the arrow is represented by some morphism F from X to Y in M. To define morphisms between such objects, we first consider the space given by all possible commutative diagrams of the form. So we have the object X, arrow F to Y, and another object X prime, arrow given by F prime to Y prime. And we have a commutative diagram which is given by two morphisms, H from X to X prime and H prime from Y to Y prime. And we assume that these H and H prime are morphisms in M and that the diagram commutes. Of course, the set of all such pairs H and H prime form a vector space. And then we define the morphisms in N from the object xfy to the object x prime f prime y prime as the quotient of this vector space by the subspace which is given by all elements in the vector space for which there exists a morphism G in M from Y to X prime, such that the composition of F prime after G is equal to H prime. And it's a standard representation theoretic fact that the category A mod is equivalent to applying this construction to the category A proch, and that this equivalence is given by sending the diagram X morphism F to Y to the cokernel of F. From this, it follows that the category N is actually equivalent to the category of all A modules. And since N was defined in terms of diagrams over A, we simply can take the action of our monoidal category C on M and define it on our category N, the category of some diagrams over M, component-wise. And since the definition is component-wise, all axioms of the module category will be satisfied in the obvious way. And in this way, we get a module category N over C, which is equivalent to A mod, and the category of projective modules is equivalent to M, because we started from M in the first place. This solves problem 4. Problem 5. Let A be a finite dimensional algebra over an algebraically closed field K. Let f, g be a pair of adjoint endofunctors of A mod with G exact. Let Pi and Pj be indecomposable projectives in A mod with simple tops Li and Lj respectively. Prove that the multiplicity of Pj as a direct summand of Fpi equals the composition multiplicity of Li in G applied to Lj. Solution. First, we note that the functor f sends projective objects to projective objects because by the assumptions it is left adjoint to an exact functor. Any functor which is left adjoint to an exact functor sends projectives to projectives. Now we can write the following adjunction identity. The dimension of the homomorphism spaces A modules from Fpi to Lj is equal to the dimension of the homomorphism space as A modules from Pi to G applied to Lj. So this is just a direct consequence of the adjointness of F and G. And now if we look at the left-hand side, we have a projective object and the dimension of the home space into simple. This gives us the multiplicity of the projective cover of this simple as a direct summand of our projective object. And in the right-hand side, we have the dimension of the home space from an indecomposable projective to some object. And this, of course, gives the composition multiplicity of the simple top of this indecomposable projective in our object. And this completes the solution of this problem. Problem 6. Let M be a finitary simple transitive D-module category. So our category curly D here, this is a category of projective bimodules over the dual numbers. Let N be the abelianization of M. Prove that the action of F, this is the projective bimodule over the dual numbers, sends any object in N to a projective object in N. Solution. If we have some object n in our category curly n, and if applying f to this object we get 0, then of course 0 is a projective object, so there is nothing to prove in this case. Therefore, we assume that f applied to n is a non-zero object in n. Let's fix some minimal projective presentation of this object. So the object f applied to n is covered by the projective object Q, and the kernel is covered by the projective object P, and the morphism is F from P to Q. And this is a minimal projective presentation. And the minimal projective presentation means that F is a radical morphism. Recall that our category curly D is rigid because F is a self-adjoint object. So we have the identity object, which is always self-adjoint, but the object F is also self-adjoint because we have the unit map, which sends 1 in the regular bimodule to x tensor 1 tensor 1 tensor 1 plus 1 tensor 1 tensor 1 tensor x. And we have the counit map, which sends 1 tensor A tensor B tensor 1 to the coefficient at x in the product A times B times 1 in the regular bimodule. It's easy to check that these two maps are unit and counit of the adjunction between F and itself. So F is a self-adjoint object, so D is a rigid category. But in particular, this means that the action of F is given by an exact endofunctor of N. And so if we apply F to our projective presentation of F applied to N, we get an exact sequence. We will get a projective presentation of F applied to F applied to N. So now if we apply F to F applied to N, this is of course isomorphic to F tensor F applied to N. And since F tensor F is F plus F, so we just get the direct sum of two copies of F applied to N. So what we have here is a projective presentation of a direct sum of two copies of F applied to N. And we also know that the matrix of coefficients of the action of f on projective modules is either 2 or 1, 1, 1, 1. So this follows from the previous problems. So this matrix is non-zero, and therefore it's either 2 or 1, 1, 1, 1. In any case, applying f to a projective object gives a direct sum of two projective objects. So the number of direct summons here doubles in each case. So we double this object and we double the direct sums here and direct sums here. But this means that this sequence is actually a direct sum of two copies of projective presentations of f applied to n. In particular, this is a minimal projective presentation of f applied to f applied to n. And therefore, the morphism capital F acting on the little f is just a direct sum of two copies of little f, which means that the ideal generated by this little f is actually stable under the action of the capital F. And so the ideal generated by the little f is, of course, stable under the action of the identity, and this shows that it's stable under the action of the capital F, so it is stable under the action of the whole monoidal category Carly D. But we assume that our module is simple transitive, so there are no proper stable ideals, and F was a radical morphism, so the ideal generated by a radical morphism is, of course, a proper ideal. So by simple transitivity, this ideal should be 0, which means that F should be the 0 map. And if in the projective presentation this map is 0, this means that this object, f applied to n, is a projective object. And this completes the solution to our problem. Problem 7. Prove that any non-zero monoidal ideal in the monoidal category Carly D contains the identity on the object f. Solution. Let little f be a non-zero endomorphism of the object capital F. So non-zero, it means that it sends a generator 1 tensor 1 of f to some non-zero element u in f. Let us tensor this little f with the identity on f both on the left and on the right. This gives us an endomorphism of the following tensor product of f with itself 3 times. So f tensor f is the following product. We take the projective bimodule tensor over d with itself, tensor over d with itself. And the little f is an endomorphism here of the middle part. All this composition decomposes into 4 copies of f. So it's f plus f plus f plus f, where the left part of f comes from this d, the right part of f comes from this d, and then we have the multiplicity space here in the middle between the tensor over k here and the tensor over k here. And this multiplicity space is 4-dimensional. Choosing any basis in this multiplicity space gives us a direct sum decomposition of f tensor f into the direct sum of 4 copies of f. So we can choose in the domain the decomposition such that 1 tensor 1 tensor 1 tensor 1 is one of the basis vectors. And in the codomain, we choose a basis such that 1 tensor u tensor 1 is one of the basis vectors. And then projecting onto the respective direct summons in the domain for the basis vector 1, 1, 1, 1, and in the codomain for the basis vector 1, u1, we will get that this morphism, identity on f, tensor identity on f, induces the identity morphism between the corresponding direct summons. And this means that the tensor ideal, which is generated by small f, contains the identity on the capital F. So this was about a non-zero endomorphism of f. Now let us look at the identity object. So it has the identity morphism, but the endomorphism space of the identity is 2-dimensional with the second basis element given by multiplication with x. And let us know that this multiplication with x actually factors through f. So we have a morphism from I to f, which sends 1 to 1 tensor x plus x tensor 1. And then we have the multiplication map from f to 1, which sends this element to 2x. So this means that the second non-trivial endomorphism of the identity factors through F. If we pre- and post-compose this with the natural surjection from F to I, given by multiplication, and then the natural embedding of I to F, given by the fact that F is an injective object in the category of bimodules, we will get that the nilpotent endomorphism of I gives rise by pre- and post-composition to a non-trivial endomorphism of F. And so using the previous slide, we will get that the ideal generated by this nilpotent endomorphism of I has the identity on F. Similarly, starting from any homomorphism from I to F or from F to I, we can pre- or post-compose this to get a non-zero endomorphism of F. So this means that the monoidal ideal generated by any non-zero morphism in Carly-D contains a non-zero endomorphism of F, and then the previous slide implies that the corresponding monoidal ideal contains the identity on F. And this completes the solution to this problem. Problem 8. Prove that Carly-D doesn't have any simple transitive module category for which the matrix M is the matrix 1, 1, 1, 1. Solution. Assume that M is such a module category. Let Carly N be the abelianization of M. Let L1 and L2 be the simple objects in N, and let P1 and P2 be the corresponding indecomposable projectives. Consider the outcome of applying F to L1 and L2. By problem 6, both these objects are projective objects in N. And by looking, so we have this matrix 1, 1, 1, 1. It's a matrix in the basis of projectives, but by problem 5, it's also a matrix in the basis of simples related to composition multiplicities. So from this, we deduce that both F applied to L1 and F applied to L2, both these objects have lengths 2, and they have one subquotient L1 and one subquotient L2. So let us assume that F applied to L1 is just unique indecomposable projective, some Pi. Here I is either 1 or 2. If we apply F again, then we know that F tensor F is F plus F, so we should just double this. So it should be Pi plus Pi. On the other hand, from our matrix, Pi is sent to P1 plus P2, and we get a contradiction. Therefore, the fact that F applied to L1 is an indecomposable projective, this is not possible. And similarly, F applied to L2 is not an indecomposable projective. So the only thing which is left is that applying F to L1 or to L2, we will get the direct sum of P1 and P2. And since we will get a module of length 2, it means that P1 is equal to L1 and P2 is equal to L2. And this means that N is actually a semi-simple category, and if N is semi-simple, then it is automatically equivalent to M. So we have a semi-simple category with two simple objects or two projective objects, so it is equivalent to the category of modules over K plus K. So in the previous problem, we proved that any non-zero monoidal ideal in Carly-D has identity on F. In our discussion here, F is given by a non-zero functor, and so the representation map from Carly-D to the category of all endomorphisms of the category M, this is injective. The identity object in Carly-D, of course, it acts as the identity functor of our category N, or M, the equivalent. And the identity functor on the category of modules over some algebra is, of course, given by tensoring with the regular bimodule over this algebra. This algebra is K plus K in our case. However, our identity object in Carly-D has a nilpotent endomorphism, which is given by multiplication with x. X squared is equal to 0. And so this nilpotent endomorphism should be sent to a non-zero nilpotent element in the center of our algebra. So our algebra is K plus K. This is abelian, so the center is again the same algebra. But this is a semi-simple basic algebra and it doesn't have important elements. So this is a contradiction. And this obtained contradiction proves the assertion of the problem. So the category M does not exist. Problem 9. Let Carly M be a simple transitive module category over Carly D such that F kills M. Prove that M is equivalent to the cell module for the cell of the identity element in Carly D. Solution. Let d tilde be the quotient of D by the monoidal ideal generated by the object F. We know that F kills M, so the same category M is then a simple transitive d tilde module category. Note that d tilde has only one indecomposable object, the class of the identity object in D. And from the solution to problem 7, we know that the non-trivial nilpotent endomorphism of the identity object in D factors through F. So it should be killed in the quotient, which means that in the quotient in d tilde, the endomorphism algebra of the identity object is K. But this simply means that d tilde is equivalent to K mod, and by problem 1 we know that K mod has 1 up to equivalent simple transitive module category. And since the cell module category for the identity object is simple transitive and is killed by F because F is left strictly bigger than the identity object, the claim follows. So this completes the solution of problem 9. Problem 10. Let Carly M be a simple transitive D-module category which is not killed by F. Prove that M is equivalent to the cell module for the left cell given by F. Solution. If we combine problem 3 and problem 8, so problem 3 says that the matrix M in this case is either 2 or 1, 1, 1, 1. And problem 8 says that 1, 1, 1, 1 case is not possible. So the only thing which is left is the case when the matrix M is just 2. So let N be the abelianization of Carly M. So Carly M has one indecomposable object and so one simple object in N. So let L be the simple object in N and let P be the indecomposable projective in N. So the action of F is non-zero and it is exact. So since there is only one simple, F applied to the simple must be a non-zero thing. We know by problem 6 that F applied to L is projective. And by problem 5, because of this matrix, F applied to L has L with composition multiplicity 2. So we have two cases. First case, F applied to L is L plus L. So in this case, P is equal to L because L plus L is projective, and so N is a semi-simple category. But then we will have exactly the same contradiction as in problem 8, because now our category N is K mod, and the endomorphism brink of the identity object in D should be injected into K, and this is absurd. So this means that this case doesn't happen, which means that F applied to L is equal to the indecomposable projective P. Now, sending the identity object I to the simple object L extends to a homomorphism from the left regular D module to Carly N by the Yoneda lemma. And from the above, we see that the additive closure of F is sent under this homomorphism to the category of projective objects in N, and this category is equivalent to M. So let us denote by phi this restriction. So this is a homomorphism from the additive closure of F inside the left regular D module to the projective objects in N, which is equivalent to M. And the kernel of phi is, of course, contained in the biggest possible kernel of such homomorphism, which is a maximal left ideal. And this is exactly the ideal which is used to define the cell representation for the cell F. So if this inclusion of the kernel of phi in the maximal left ideal were proper, this would mean that the dimension of the endomorphism algebra of F applied to L would be strictly greater than this dimension in the cell module. But in the cell module, the dimension is 2, and in our case, the dimension is also 2. So since the dimensions coincide, the kernel of F coincides with this maximal left ideal. In particular, phi factors through the cell module and in this way induces an equivalence between the cell module and M. And this completes the solution. Some problems and questions at the end. Question 1. Check all details in the claims that A mod is equivalent to the Abelianization of A proch. Question 2. Prove an analog of problem 6 with projective changed to injective. Question 3. Explain with full details the argument in problem 9 claiming that d tilde is monoidally equivalent to K mod. Question 4. Describe all monoidal ideals in D and in the analog of D for Kx modulo x cubed. And question 5. Classify all simple transitive module categories over the monoidal category of projective bimodules over Kx modulo x cubed. Thank you very much and see you next time.